Welcome, and thanks again for joining us for this webinar. I'm Washington Wedderburn, Product Manager with the Digital Mission Engineering Business Unit at AGI. And this is my colleague, or sometimes partner in crime, JP Plushnisnik. And JP is our Technical Director for Sensor Systems at AGI. And today we're going to dig a little bit deeper into the newest release of the RF Channel Modeler. Radar signature analysis is both the art and science of understanding how radar signals interact with complex targets to expose the various scattered radar returns. Radar images are not literal images as generated by electro-optical and infrared sensors, but rather they are a mapping of radar scattering returns in range and Doppler space. Ansys is enhancing RF Channel Modeler to create synthetic radar data for any collection geometry or geospatial domain to support both synthetic aperture radar, SAR, and inverse SAR data generation. This will merge Systems Toolkit SDK to define the collection scenario and Ansys Perceive EM to seamlessly support synthetic data generation in the rawest data format, INQ data. This data can then be processed appropriately to create all data associated with the collection scenario: frequency response, range time intensity, Doppler time intensity, and wideband radar images. This complex data and corresponding products will support data analysts for event recreation and training, collection planners to optimize expensive test plans, and the development of AI/ML algorithms requiring massive amounts of realistic signature data. Critically, RFCM radar leverages GPU acceleration to create data in near real time. Okay, JP, so why don't you give us a little bit of a refresher on what RFCM actually does?
Okay. Well, thank you, Wash, and thank you for participating in the webinar. Again, the RF Channel Modeler, and we refer to it as RFCM, so throughout the presentation I may go ahead and hop back and forth with that. Came out earlier this year. The first version, first release was specifically focused on communication. And what you're going to talk about today is the second release, which came out in July of this year, I think, for being able to process and generate radar images, okay? Let me go ahead and also, during the presentation, I'm going to go ahead and show you some stuff from the screen to kind of capture the information, but I think it's very important that you understand the product is still the same product. Okay, there's nothing really new inside there except for the look and feel and how we actually feed information into the system, which is going to be focused on radar type scenarios, and also some of the outputs. So we can actually generate some of the wideband images that we're trying to show off for the system. So what is the RF Channel Modeler? So the components of RF Channel Modeler, if you look at your screen here, is we have STK, Systems Toolkit, which becomes the primary orchestration piece of RFCM. Perceive EM, the solver itself, comes from our Ansys electronics unit, which is the actual data generation system. And that will be the primary source of data generation that comes out of RFCM. But we use STK to prepare the data to go into the system and also STK to present the data afterwards. This is really very interesting because the data we're going to talk about today is very, very complex data, very high resolution model data for not only the scenes, but for the targets. We also bring in our antenna data, our Ansys FFD format, or even just some basic parametric antennas. But STK orchestrates all that information. Make sure that everything that goes into Perceive EM is properly positioned, moves the right way, turns the right way, and we go ahead and ask Perceive EM to generate data that when it comes out, it will go ahead and generate that raw data you just mentioned, the INQ data that we need to process to make the images. So let me also go ahead and step down to the next slide. Okay, I'm going to build out this slide. You saw this previously with Sean Carpenter back in January, where he talked about what is the real basis of the RF Channel Modeler. And really what's important here is trying to characterize everything that happens from transmitter to the receiver. We use STK to locate the transmitter, locate the receiver, and we also use STK to put all the pieces of that chessboard down, all the components, the buildings, the vehicles, the aircraft, the satellites. But in comms, they're worried very much about trying to understand how energy propagates from transmitter to receiver when you have the antenna gain patterns, the movement of the vehicle, looking at the actual scene, and they're trying to characterize that channel from antenna to antenna. I'm trying to show you the channel with radar data. I have the exact same information, that scattering data, that the scattering matrix. We go ahead and use that to help understand signal flow for comms. But for radar data, I can show you where things scatter both in range and also in Doppler, which generates our wideband images. What we don't do in RF channel modeling, even in the past or even now at this stage, is actually put in the radios. In comms, they want to put in the radio, send a certain signal through that you can hopefully see on the receive side. Various vendors, MATLAB, Keysight, other tools, they're very good at building out these radios, but they don't really have a good way of characterizing that channel model, you know? And that's what we're doing right now with RFCM. What I'm going to be doing now is taking a transmitter receiver, either put it in a monostatic or also in the bistatic scenario, and show you what actually is scattering in that scene. Like that's the whole key part of this system. So we're selling you the wireless channel modeling piece here, but in the future, if you want to add your own radios, your own waveforms, you can add that also on your own. And last of all, let me show you a fast build out. Again, the important part about all this is the scene data, putting that scene into STK, the buildings, the vehicles, having them moving independently, the antennas, where they're located, either if it's going to be on a tower, it's going to be on a vehicle, in a quadcopter, person on the ground, big radar on top of a building, satellites flying overhead, whatever it is, that scenario will be orchestrated by STK. We're going to then send in our signals into that environment, characterize the entire environment. Out comes the INQ data that you mentioned earlier, to generate that frequency response for everything between a transmitter and receiver. Then if you go ahead and do an inverse Fourier transform, you generate that range response. The same time delay that Sean had in his data, I also see as a range response to scatterers, how they appear in range. And when you process a bunch of those pulses, you do a Fourier transform across each range band, we generate these wideband images, and we'll talk more about that throughout the webinar presentation.
Awesome. This is awesome. So you know, what led to the development of RF Channel Modeler? Why did we decide to go down this path a year ago?
I was a pain in the butt. Okay? Well, yeah, but what happened was I came on board in 2021. Okay, and I love the STK product. It's helped me out over 30 years, right? And then when Ansys acquired AGI, Ansys came with a plethora of solvers, fantastic solvers across the entire electromagnetic spectrum. And part of their goal is to bring these systems together. And during my early discussions with Sean Carpenter, even during the interview, right, I think he saw that he had somebody in AGI that can now help bridge the two tools, the Perceive EM tool and STK, because STK can help customers see what they're doing, okay, where Perceive EM helps you generate the data. So what did we do? In 2022, we started making slide decks and started pitching this to our leadership. It was a tough battle. I mean, you guys were very, very nice, but you made it hard. But I'm kind of annoying, okay? And sure enough, Shashank would agree with that statement, right? And then we had to go ahead and prove our wares. And luckily, the folks, Sean, in the 5G world, and first RFCM, is really going to benefit by this. Okay, these guys, we have certain customers, can't talk about them here, but they're already tearing into this data, and they use that raw data with their own tools to exploit it further. But we decided to go ahead and make this product available because people were questioning whether Ansys could actually do this, and that was a driving factor. And we knew there was potential customers, not only in the comms world, but also in the radar world. So last year in 2023, we had our first year where we actually built out the first product line, and then we started the second release, and which is now released in July of 2024.
Excellent. So, you know, what's the special sauce that makes RFCM different from any other tool out there?
Well, I guess it's like Ansys really does go ahead and allow this to go ahead and exist, not only because we have now a DME set of tools, we have these solvers, and putting them together, that's one part of it. But the Perceive EM solver, and I'll give extra credit to the folks in the electronics group. They got a fantastic solver. These people came out of that same world, the X-patch world, with the shooting, bouncing rays, physical optics analysis, and they've taken their version of that, and as they came into Ansys and they refined that product, it is a shooting, bouncing ray solution, but it also does physical optics. And what do I mean by that? We illuminate every facet in the scene. Millions of facets in the scene. We identify which ones receive the actual energy. Then we go ahead and characterize the actual surface current on that facet, either from the incident field or from a reflected field. Then that current on a surface, you can then go ahead and propagate it to the receiver in combination with every other facet that can be seen by the receiver, such as physical optics, Green's theory calculation. And that happens in other tools too, but we actually do it very, very fast because our folks focused on the GPU acceleration techniques, and we also put it on the NVIDIA graphics cards. So this stuff happens lightning fast. Depends. The larger the scenes, you're talking about seconds to go ahead and generate massive scenes. Vehicles, we crank out. I mean, those things are done in under a second sometimes, okay? So it's near real time. I don't want to say real time because you put a 10 million facet scene, it's not going to happen for you. We spend more time just making the images than generating the data, okay?
So let's say you do have a scenario where you have potentially thousands of objects that are generating returns. What are your options for actually scaling that type of problem?
Great question. And the thing is, of course, our Ansys leadership is always happy to go ahead and offer up an extension to our current tool set. Our initial goal was to make sure that we had a tool that worked properly and it showed the full functionality between the digital mission engineer environment to go ahead and build out the scenario and running that tool. But the good news is PerceiveEM is an API. It runs on a network, right, on the cloud. So in the future, as our customers get more and more demanding with larger and larger scenes, we'll be able to go ahead and scale up and actually go ahead and run multiple instances in parallel. It's a naturally inherent parallel process, okay? So the only thing is, if your demand requires faster solutions, we can go ahead and spin up more HPC servers with the software, generate data. You'll probably have more problems just storing the data than you will be generating the data, okay? Because it's lightning fast and it fills up that memory very, very quickly. So that's where we're going to go with
Awesome. All right. So initially, we mentioned ISAR and SAR. Can you talk a little bit about what the actual differences are?
Yes, I can.
Is there anything you can't talk about?
Yeah. I forgot about those things, right? So, but the whole world, ISAR and SAR, it's all about wideband imaging, just so you know. Okay, people are very familiar with the term SAR because they see stuff nowadays online with synthetic aperture radar, and that typically gets tied to things like, I'm going to go ahead and look down on some spot on ground. I'm showing you a picture right now, the planes flying around or a satellite. We then go ahead and characterize that antenna gain pattern, and what you're seeing is SAR is typically looking down at these large city scenes, cityscapes. You see these large returns from buildings and everything. So SAR, synthetic aperture radar, is tied to looking at big landscape models, and then when you look at ISAR, it's typically looking at objects. Okay, I try to explain it as SAR is when the sensor is moving around the vehicle, and ISAR is when the vehicle is moving around the sensor. But that doesn't always the case because I could be doing a SAR image and there's a vehicle moving in the scene. So is that ISAR side? It's all really wideband imaging, just so you know. Okay.
Got it. So we talked a little bit about the combination of SDK and PerceiveEM to come up with the RF Channel Modeler. Yeah. Can you talk a little bit more about how SDK is invaluable in this process?
Yeah. So again, the solution is a combined solution. RF Channel Modeler. PerceiveEM by itself is its own product too. You can also buy PerceiveEM by itself. It's a very powerful API, and we're always happy to help our customers out who want to go ahead and develop their own solutions. But everybody has the same issue. I have to feed my solution with content, which is usually geo-referenced content. And SDK is the premier software that lets you go ahead and generate that mission environment. So in SDK, of course, we go ahead and do the transmitter location, receiver location, the scenes, the vehicles, and how they move around. I already mentioned that before. But then you have to go ahead and move those pieces in the scene, and that adds velocities and motions, right? So in this one example I'm showing you now is going to be a one for a scenario where the ground-based system is tracking a satellite. And SDK is great at not only positioning where that satellite is, but you look on the right-hand side, it also captures the motion of that satellite, how it pitches, yaws, and rolls. And we also capture the motion of the sensor on the left-hand side. You see how it moves, how I maintain the vertical and the horizontal polarization. That's all important to the real people who want to look at their data in a real way. What happens to my polarization? What happens to my sensor? That all can be captured and driven from SDK to per CVM. So SDK is a very, very important part of helping you orchestrate that system, right? Next one's going to be, and then that data, that front end data that goes into per CVM, drive data generation. Then we'll go back to SDK to put that data back in it to understand how to interpret that information. In this scenario here, we're actually setting up the template of where I want my data to go. You're going to see in the next couple minutes, I'm actually going to show the results of that radar image and put it onto the plane, because I am telling you, based on the motion of the sensor, based on the motion of the vehicle, it generates these angular velocities, which dictate how to interpret the data. The next part is SDK makes that easy. It's all inside there. And anybody who's more interested in that will be happy to go ahead and show you some more about that. Let me see next here. Okay, so again, orchestration, SDK is fantastic at flying the vehicles, identifying the sensors. And I already showed you this before, but it's a very powerful slide because we actually allow you to put in that intended gain pattern, which dictates how the intensity of the rays that we shoot in the solver, right, in that direction. All right.
Awesome. So do you actually need SDK to feed per CVM? Or can you just simply use per CVM on its own? Like, what are the benefits?
Yeah, I think we kind of talked about it a little bit, okay? But I think most people that we deal with right now, they just love the fact that you can get and control that data coming in. In the following slide here, again, what you're seeing right now is that center data set is actually what comes out of per CVM. That's actually that raw radar data. It's processed once to give you the range profiles. But we also use SDK to identify the viewing geometries, how the sensor moves, how the targets move, and then we steer the antennas that are used in per CVM to generate that data. Then, when you have that data, let me go ahead and look at this. That data gets put onto these planes to help you understand that. So SDK does become the bookends. Yeah, I mean, so you can see controlling information goes into per CVM, looking at the results to understand how that actually goes, how that actually moves. In this one scenario, it's really exciting here. I'll show you right in the middle here. This is the plane flying nice and level, and it's turning rather slowly, so it's easy to process the data. But watch in the center over here, when the plane does a aileron roll, the plane, that red plane, snapped into position because that angular velocity dictates how to interpret the data. You don't get that with per CVM. You get that with SDK in the RF Channel Modeler, okay? So, but the results out of here, the little radar images, are actually coming from per CVM, so always very excited about that. And the same thing happens for satellite data. In the satellite world, same thing. I'm gonna be flying by a ground system. Here's that data up top from per CVM. You process the data. I can give you a little glimpse of that radar data as being processed. We grab X number of pulses based on how fast it rotates in your PRF. We'll go ahead and make that radar image. You're actually getting a little bit further view in this picture here. I'm going to show you this next to the satellite, but this is the radar image that comes out of the system based on what you pick. You now have to put that on top of the model. And how do you put it on top of the model? You basically put it into the SDK scenario. We tell you how to paste it on there based on the actual collection geometry. And what you're going to see now is that data, and you'll see that red plane hop around. It's a really cool view. But it's very important because I now use SDK to understand the angular velocity vectors relative to the collection system that will allow you to align that image plane. Let me move this a little faster here. You're going to see as I slide along here, you'll see a plane. It'll start snapping in place as the bird moves, and now it's staring at something on the ground. It'll pass by, and then you'll see as it moves quickly again, it will all of a sudden snap back in a different location. Here it goes, watch. and then back again to staring off in the distance. Very, very powerful capability.
Excellent stuff. So we've seen a little bit of this in the different videos that you've already shown, but what physical domains are we able to play in with the RF Channel Modeler here?
Yeah, for both the comms and also for the radar world, one thing that AGI really wants to make sure is that we don't solve one problem, we solve many problems. If we're going to spend time adding a capability into the system, we try to make it as agnostic as possible. So in this specific case right now, we made sure we built it so it doesn't matter where the transmitter is, where the sensor is. On the left-hand side, we're showing you can do from space to air to ground, looking at targets in space and air and ground. And the data is that wideband data. The ISAR data can be generated or the SAR data can be generated very, very simply. It's fully agnostic, whether you're looking up, looking down, looking across. Okay?
Excellent. All right. So one of the things that jumps out is so far as a very critical element in doing this type of analysis is the ability to have highly detailed, accurate model representations, not just the vehicles, but things like buildings, terrain. So for customers out there who want to actually do this, does Ansys provide those models for doing these types of analyses?
Yes and no. Okay. We use our models in SDK for visual sake, right? You want to be able to see that object in the scene. And we have our tile with the Cesium 3D tiles, also our visual models. And I think a couple years ago, they made a decision to go to a GLTF format, okay? So AGI has a series of models they already have in their arsenal, okay? But they're not going to be all the models that you want for your projects. So when you come into this this tool and you want to show your model in that scenario, make sure that you go ahead and bring it in a GLTF model format. We can go ahead and convert STLs and also OBJs, but the GLTF is a very, very unique model format, and we'll talk about another benefit in the next couple questions. The models themselves, when you look at these models, let me show you. In this case here, we have some models, and the important part about these models is I'm showing you only 5 of them, and these 5 are going to be important in the next month or so, but right now, let me show you. We have the ability to put that inside there, recreate that viewing geometry, and actually go ahead and do the collections on those models to generate that synthetic data for that individual vehicle. That GLTF model format is a very, very nice, powerful format. You can buy models online if you want to go out to TurboSquid and the various vendors, but most of our customers are probably going to have access to their own set of models. But until you go ahead and learn, if you're trying to go ahead and do some examples of what SAR can do for you or an ISAR, you can go ahead and turn to the models that we have available for you. The next one is the 3D tiles. 3D tiles, okay, are extremely powerful ways of presenting this photogrammetry data. AGI and Cesium, they created the 3D tile format, and it's even being adopted today by Google, which is a really, really big deal. Getting this data is very difficult, okay? There are some great vendors out there, okay? A company called Aerometrics. This is actually our data, but a lot of the stuff that I've generated right now in some of the data slides that I have, and also in some of the presentations at conferences, we use the Aerometrics data set, and that's because it's extremely high resolution, 5 centimeters, 2 centimeters, and street level type resolution, and it's surreal. Not only do you put the imagery on top of it, but you actually have a good physical representation of various cities, buildings, and it all comes down to having very, very good data, right? So in this case here, we're going to show you, this is the Aerometrics data. This is our Denver scene. Fantastic. I recommend you go ahead and reach out to talk to Jeremy Pollard at Aerometrics, and we'll be happy to set you up if you have more questions about what kind of data sets you can acquire from them. But this is beautiful data sets. We went ahead and used Denver also. This is the football stadium. And I'll show you some results from this, but you need, depends on your frequency, depends on your bandwidth, but it's always good to have high resolution data if your computer can handle it. Guess what? Our algorithms can handle the high resolution data. And OpenStreetMaps may appear to be a real nice solution, but and I'm not going to bust OpenStreetMaps, okay, because they have a very important job also. With OpenStreetMaps, you can't generate data that's going to look like this from something like this, right? So it depends on what you want to accomplish, but in most of our cases, you need some high resolution photogrammetry data. If you ever want to accomplish something like this, you'll see the aerometrics data here spinning around 360 degrees. Look on the right-hand side. I mean, not only do you get the shadowing, but you actually get the characteristic scattering response from a realistic representation of that scene. Very, very powerful data.
Aerometrics has really been great with providing us with some really high quality data for us to use in a lot of our demos. So definitely, if anyone's interested, we'll certainly help you.
And cesium too. I'm telling you right now, cesium is becoming a warehouse, okay, to let you go ahead and go in there and show the cesium ion platform. Even the aerometrics guys use cesium ion to show their data, right? So it's a great venue to show your wares in photogrammetry. But getting good data, I think if Google ever, and we asked them if they would ever go ahead and release and give us authorization to use our data analytically as opposed to just visually, you would have access to about 25 or 3,000 cities around the globe. The resolution, though, it varies, okay? And I can tell you my experience being out there. I'm not trying to go ahead and promote any one vendor, but I think you have to really go ahead and look at the resolution if it's going to meet your needs to go ahead and model this data accurately.
Okay, so that leads me to my next question. As far as the material properties associated with the 3D tiles, are we able to take that into account when doing these types of analyses?
Well, the answer to that question is always yes, okay? So we can go ahead and handle materials. And talking to Alex Wood this morning, and he's got a lot of great new capabilities for us, right? So Alex, we look forward to your next features. But at this stage, what happens is we actually assign material content to the entire model. So if you want to have that model have other material, asphalt or concrete or plastic or glass, you would actually break apart that model, maybe using Blender, and define those components as having different material. That being said, and it does work fantastic. So the only thing is you have this glob of individual models that behave all the same. So it looks like one model, but the reality is, like helicopters, I have blades turning that are different material as opposed to the body. What we're going to do in the future, and what GLTF format is very, very good at, is it lets you assign a material index for every facet. Okay, and if you look at the photogrammetry data, you see it looks like a real image on there, right? Because it is an image map to it. Our cesium folks are actually working on a artificial intelligence routine that will interpret the image and assign a material index to the corresponding facet under that. That's going to be phenomenal, okay? Because everybody wants to handle materials, okay? So we are going to go ahead and continue doing what we're doing. Our goal is to let you create realistic scenes, but in the future, you will have access to facet level type characterization for the materials.
Excellent. Anything we can do to reduce the amount of manual intervention that the user has to do go a long way.
At the beginning, when we started this whole process, one of my slides was the 800-pound gorilla in the room is we have the most powerful tools. Where is the data? Okay, so there's a market out there, and people do go ahead and try to provide those models to the customers. And in certain government locations, they probably have access to data sets, but everybody assumes, oh, everybody has this stuff, and guess what? No, everybody does not have this stuff. Okay, so go out there, and then we'll be happy to help you out, make some contacts with some of these vendors that we found to be very, very qualified in generating this high-resolution data.
Oh, awesome. All right. So, we refer to the output, as being like real radar data, right? So, how real is real? What do we mean by that?
It's real.
It's really, really real.
Yeah, it's really, really real. So what does that mean? Okay, now if you see some people make some like SAR images, they'll usually work in the graphical world and have these beautiful models, and they say, we're going to make these pixelated pictures that look just like the ones, so you can play with them, right? And that's fine for helping people like look at what a SAR image may look like. We use STK to orchestrate all the models, all the facets, and then with PerceiveEM, we go ahead and generate frequency response data for every viewing geometry, okay? So the next slide you're going to see right now this is an example of looking at an aircraft, okay? And when we send we go ahead and orient that object in our scene, and we go ahead and sweep over that object from a low frequency to a high frequency, I'm generating a thing called a frequency response. And as I change the angle or the orientation, I generate a new frequency response. That data is about as clean as you will ever get from any kind of analysis, okay? For any, even real measurements, it's very, very difficult to go ahead and go in outdoor ranges and worry about clutter. This is going to be just a pure response, and it's limited by the resolution of the model and also what the actual algorithm can generate. Okay, a shooting mounting arrays has limitations also, okay? But for high frequency solutions, electrically large scenarios, short wavelength with large, we generate some very, very nice data. We generate it fast. The frequency response data is basically saying, what does my model look like at this viewing geometry for this one frequency, and then the next frequency, and then the next frequency? So when we look at this actual one specific data set, I have a model, and I'm also going to have a scene. Okay, for us, we don't care what it is. Okay, we define the bounds, how much unambiguous range, how unambiguous cross range, or unambiguous Doppler. Those are settings which let you adjust the parameters. How many frequency steps do I want to take? How many pulses do I have to combine to make an image? And they vary based on the size of data that you want. In this case here, it's a relatively small, it's probably a 50-meter type window that we care about in both range and cross range. So I'm going to scan through a bunch of frequencies and get the frequency response. Out of viewing geometry, I'm going to step to the frequencies. In the real world, they generate a linear FM pulse, which is basically a scan from low to high. And they actually, out of the linear FM system, they actually generate the range response. That's a compressed data coming out first. But we can generate our data to recreate that range response also for them. And that is your raw INQ data. In phase and quadrature, real and imaginary magnitude and phase, however you want to define that. We give you the full complex data sets. So you have that raw data, you can process it anyway. You can then go ahead and actually make your images based on what you know to be the motion of the vehicle and picking the right number of pulses, and then you can go ahead and generate these beautiful wideband images. In the real world, you also have to do pulse alignment, okay? We are actually doing some of that for you because our goal is to get you good images fast, okay? But some customers said, keep them as messy as the real world is. So we're gonna actually have to add in that ability to show you what happens in the real absolute collection. That's going to come out in the future, you know. I mean, I already talked to the development team on the Perceive EM side, so they can generate that data from pulse to pulse based on a real location. So not only do you have the model, but you also have the scenes. Now the scene gets even bigger. This is a 750 meter by 750 meter scene. It's a very large number of facets. I think it's about probably 5. I think Nate went ahead and did this 2 years ago just for me. He knew this was going to happen. See, it's amazing. Very influential person that I am. But the nice part about this is this model lets you go ahead and look at any view, and I can now drop pieces inside there and move them. And we don't play games with it. We just say, here's what you got. Give me the data. Give me the frequency response. And when you process it, I'm going to show you some data later on that's absolutely eye-watering because you actually characterize the motion of the vehicle because you're trying to interpret the non-moving buildings, but the cars and the planes, they're all moving. Right. And if they're moving, they have to be mapped to a new location. It's a map. Remember, you said before at the beginning, it's a radar mapping, all right?
This is all great stuff, obviously, and we think there are tons of use cases out there. But you know, who are the primary targets? You know, who's going to benefit the most from having this type of capability at their fingertips?
Yeah, that's a big question, right? Who really cares about this stuff? Who's willing to go ahead and pay for it, right? I mean, I know our leadership cares about it because we help make money out of it. But the reality is we want to make sure customers benefit by this. So who are the three primary customers? And I always have three groups of people. And the first one's going to be your intelligence or your data analyst. What do I mean by that? Radar signature data exploitation is complex, requires a lot of training, a lot of understanding. A SAR image is not an electro-optical image, like you said in your introduction. It's actually a radar scattering map. So this is a powerful tool to use just notional data, very nice scenes, representative scenes, city scenes, country scenes, vehicles in the fields, vehicles in the air, to help people understand when they see a radar image, they now can say, I understand what's going on, or I think the following thing is happening. Well, then go into that software and recreate what you think is going on and see if you get the same results. It becomes a very nice validating source, training source for those analysts, and helps them go ahead and maybe understand their real data exploitation. Collection planning, next important customer. So there's two kinds of collection planning I'm trying to support here. There's cooperative collection and non-cooperative collection. Let's talk cooperative collection first. Cooperative collection is, I'm about to spend $1 million, $2 million at a test range. I got a brand new super duper high-fangled fighter, okay? I only have range time for the next week. I don't want to miss any days. Why don't you just go ahead and fly the thing synthetically? Where should the sensors be? Whether it's optical sensor, whether it's radar sensors, if you worry about electromagnetic emissions in the comms portion of this, because you may have to worry about having multi-path nulls in your data that you didn't realize was there until after you get the data and review it, and you're saying, I just wasted $1 million of test range time. Those test range sites are very, very resource limited. A lot of people want access to that test range. It affects programs, so getting on the schedule is very important. Make sure that your time on that schedule is 100% successful. Non-cooperative collection, I'm about to go ahead and look over a border into a country to see what I think is going to happen. I hear they're going to do a certain test tomorrow. Where should you put your sensor to get the best possible data? Very easy to go ahead and model that, right? And last of all, and not least of all, is the artificial and machine learning community, okay? Artificial intelligence. The artificial intelligence world right now is the biggest buzzword right now in Washington, D.C., right? If you wanted to go ahead and sell donuts, Wash, you call them artificial intelligence donuts, and you'll go ahead and put Dunkin' Donuts out of business, okay?
Time to make the donuts.
Yeah. But if you ask the artificial intelligence expert, what do they say? What's the biggest problem that you have? Lack of data, okay? At least for the routines that we have right now. There's new stuff coming out, but the reality is if you want to train a system, you have to train it with a lot of data to account for all the different variations and make sure you have good, clean data. We have the ability to generate synthetic, wonderful, beautiful data. And that data can then be used to train your systems. I have some slides afterwards I can actually show you from stuff that we're doing. And we'll talk more about the next question. But in this case here, artificial intelligence, you can go out there, put your models inside there, put them into an environment to see whether or not your algorithm works based on how it was trained, okay? And that can generate an endless amount of data. I can fill that data lake. Right? Okay.
And that's a critical function there. I mean, the last thing you want to do is train your system on bad data, right?
Yeah.
And then you don't know until you get out in the real world, and your training data doesn't match actually what you're going to see in the real world. So, very important that you have tons of data to do that training on, which kind of leads into my next question here. We're never satisfied, right? You know, it's always, what have you done for me lately?
You guys are brutal.
So in that context, what do we have to look forward to next?
There's always a lot of improvements. People want to add certain features, but this is a brand new product. Came out in spring of 2024, and now the radar portion is coming out. It's come out now in July. So we felt it was very, very important, okay, to give our customers something to think about. Okay, so let me go ahead and start my next slide, and let me just hopefully your microphone's on, right? But the reality is called Project Loch Ness. And why do I call it Loch Ness? And also, I'm sorry I'm jumping around, but the reality is in the next couple of weeks, you're going to hear about Project Loch Ness. Keep an open ear about it, okay, because what we're saying is in the RFCM world, for you to go ahead and assume that we're going to buy your product, we trust everything's great, that's all wonderful, but the reality is I want to give you some data and let you play with the data. On that last customer use case, who benefits most, the artificial intelligence community, we realize they need very, very good data. I'm going to generate that data lake for you, and we're going to do it for free, okay? And when I say it's free, I'm giving you a comprehensive data set on 5 separate targets and a series of scenes with those targets in the scenes, so you can train and validate your data. Okay, I think I have some additional slides to go ahead and show. Again, this is an example of the kind of stuff you would expect to get. This is not Loch Ness, okay? This is our data from Aerometrics from the stadium. But inside these, we have these vehicles in that scene. In the real world, you will have vehicles in your scene. They're expecting the artificial intelligence algorithm just to go out there and find us in the scene, right? So when you go ahead and generate your first data set, okay, we're gonna talk about this next, but this is going to be an example of the kind of data set you would have. You have to find those vehicles in a scene, but how do you train those systems? We also will go ahead and give you those models, and the data, we'll give you the data from those models so you can train your system at all the various viewing geometries and around 360 degrees, and we'll also generate data sets that you can go ahead and now see and validate whether your algorithm can find those objects, because it's the exact same model in that scene. So that's going to come very, very soon. The one thing that's really, really mind-blowing, and this, the people ask, well, is your data good? Does it really, really good represent reality? And this is where I mentioned before, this is a close-in view of the one scene you'll see over here. Watch this. You see the planes moving on the bottom left-hand side of the screen, coming towards you and away from you. Those now have Doppler. Every aircraft in a scene is off the ground and it casts a shadow. Okay? So when you look right now, aircraft 4, aircraft 5, they're actually moving. If you look at this part of the scene, I don't know if you can see it over there, but you're going to see the shadow of this aircraft is where the aircraft is actually located. This aircraft is actually over here. This aircraft is actually over this shadow because it's hiding the ground. There's no response. But the scattering coming off the vehicle actually has negative Doppler, and it moves it to the left. And the other one's coming towards me, positive. It's moving to the right. And the distance between those is the actual meters per second. Down the bottom, you can measure those, of how the energy comes towards that radar system. So you can actually calculate what that thing is doing on the ground. Okay? And we can do this in a video SAR mode. People talk about video SAR. Well, guess what? I can generate all the movies you want. Okay, it's very, very simple. So you'll be able to do it also. Okay, but right now, for the purpose of the whole Loch Ness world, we're going to give you that raw data sets from each of the aircraft, the data set with the aircraft in the scenes. I'm going to tell you everything, what's going on in that scene, so you can validate your results. Okay, so I think that's should be hopefully interesting for you to go ahead and look at.
Excellent. Well, certainly looking forward to lots of participation in Project Loch Ness. I think that'll be some exciting opportunities for us to collaborate with some of our customers.
And Ansys is trying to go ahead and give the community something. We're trying to be, that, can we help out the artificial intelligence community? Okay? Yeah. Everybody's in on it. Everybody likes artificial intelligence. It has value. Ansys GPT. I mean, we all have our tools. But artificial intelligence help you trying to exploit your data, help guide the analysts. Very, very important that, and if we feel our solutions are so good that you'll love them, we'll give you data right now for free to validate your, our tools are going to be able to help you out. All right.
Excellent. Excellent. All right. Well, thank you for all that, JP. That was
always a
very
pleasure.
Entertaining and educational at
always
the same time.
Exciting, yes.
All right. So at this point, we're going to open up the floor for questions. Anyone has questions, feel free to put them in the chat, and we'll do our best to respond to those.
We're going to take a little break first. We're going to transport ourselves to a brand new location. Yeah. That's what you have to do, right? So when you see us, okay, in the questions answered, I'm sorry, but we're going to be moving so fast. We'll be ready to go ahead and answer those questions in a different venue.
Absolutely.